Okay, let's focus first on what is the aim of this course. The aim of this course is to give a phenomenological approach to materials. First, we must distinguish between what is understood by material science and by materials engineering. Both disciplines are quite tied together. I mean, we cannot separate them completely. But it's true that the focus or the way to proceed in one and other side of this scheme is different. This scheme is known as the materials tetrahedron and is used quite frequently to focus to remark the main objects or the main topics in different aspects of materials, either science or engineering. As a common point for both approaches, science and engineering, I have put here composition and properties. If we focus on the engineering part, then we'll be dealing more with yield, cost, synthesis, processing, design of product, life cycle, recycling, all these more technological aspect. If we go to the other part, here to the part of science, then we'll work on the composition, properties of course, and we introduce something new, which is the microstructure. That means we are going also to consider how the different parts, different atoms, different phases of the materials are arranged to give the macroscopic solid we are looking at. We are talking about material science, and that's because materials is a cross-cutting discipline. We cannot separate different science in the frame of materials. It's not so easy to separate material chemistry from material physics or even from materials biology. In our case, we are going to focus more on the materials physics, even if, as I have just told, it's not always so easy to separate or to define the boundaries between materials chemistry and material physics, for instance. In any case, we are going to concentrate on these compositional properties and microstructure and see how both aspects of the materials are related to give us the materials we normally use. As an example, I've used the endoscope. Endoscope is an example in which, at the first sight, you would never thought that materials play an important role there. However, in a modern endoscope, you have an optical fiber. That means you need a material with a very well-defined refractive index and very good transmission properties. Then you have coupled light. Typically, currently, we use LID, so diodes. Then you need semiconductor materials that allow us to fabricate these optoelectronic devices. And also, we need something to make the image. Typically, we use a CCD camera to catch the images from the body, from the hollow cavities in the body in which the endoscope is introduced. So these images are sent directly to a computer, and the computer will process the images, digital images will process, and then will be passed to the physicians so that they can interpret what is happening there. And then behind all these things, the LID, the CCD camera, or the optical fiber, beside these three things, great advances in materials have been required. Okay? Of course, before this final design we already know from the endoscope, there were some other examples. The first known endoscope comes from the beginning of the 19th century. It was designed by Pozzini, and you see here it seems to be a little bit rougher than the modern endoscope. So you see here as illumination source. We don't have a LED, but candle. Here we have two binoculars to observe what is happening, and here is the part, also of course no optical fiber, no transmission of images, just human eye looking through these lenses, the candle, and this is the part that was introduced into the body. Later in the 17th century, the Salmon developed something easier. It's not so rough, so to say. Instead of a candle, then we have an oil lamp. Here we have already a set of mirrors that permits a better observation of what is happening inside the body, and still we have here the part that it's introduced in the body. And then finally, at the end of this century, so it was relatively rapid development, at the end of the 19th century, then we have this kind of tube, then it's much thinner. It's not this one, but much thinner than of course the previous one. It is broken to indicate that it was longer than it's shown here, and that was designed by Nietzsche at the end of the 19th century. Let's come back to the materials tetrahedron and consider the difference with two different examples. I could select many other examples, but I have selected one of the group which normally is considered or normally labeled as structural materials, and another example from the typically labeled as functional materials. In the case of structural materials, I have selected automotive steels, and for functional materials, polymeric semiconductors. In the case of the automotive steels, then we have, if we look for properties, composition, or for microstructure, that's the more scientific part. Then we have alleles, proportions, major elements. If we look for microstructure, then we have to look for phase distribution, the influence on mechanical properties of this phase distribution, which is vital for the structural materials. And if we go more for the engineering part, then we must take care of the different procedures to fabricate or to produce the steel in such a way that we get the maximum toughness and formability. And also an important factor, of course, the strength. For a car, we need something which is robust, but as important as the strength, or even more in some cases, is the strength to density ratio. The lighter, the better, as far as we preserve, of course, the physical integrity. Then we must look also for formability or for cost. Let's go to the other part of the scheme. Now, a polymeric semiconductor. Of course, not all polymers are adequate to fabricate a polymeric semiconductor. Then we must check what polymers and which dopants are suitable for fabricating such a material. Also, we must consider the nature of the bonds and their influence in the properties, and in particular, since we are focusing on polymeric semiconductors, and in particular the influence on the conductivity of the material. And of course, if we go to the more engineering part, then manufacture films, circuit printing or circuit creation, what are the electrical characteristics of the material, working conditions, sturdiness or manufacturing cost. And talking about manufacturing cost, in this particular case, it's particularly important to consider the manufacturing cost with respect to the current technology, which is silicon technology. Yeah? We have been talking about two different, or we have said somehow, when we go to the scientific part, to the material science side of the tetrahedron, we have put the focus in the property and the structure. What are these two concepts? Okay, if we go for property, Property is the response of a material to any external stimulus. Mechanical, electrical, optical, magnetic, any stimulus. I mean, you apply a stimulus to a material and the material will defend itself or will respond to this stimulus, which is what mediates this response, the property of the material. Mechanical properties, electrical properties, or whatever. Sorry. In the case of the structure refers to the arrangement of the internal components of the material. Depending on the scale we are looking at or we are moving in, then we'll talk about subatomic structure, or atomic, or microscopic, or macroscopic. I mean, we can go for the structure of the atoms, then subatomic. We can look at how these atoms are arranged to form a crystal. For instance, here is represented a sodium chloride crystal. Or we can see how these elemental units of a crystal arrange to form a little bigger structures, not much, so microscopic crystals. And if we put together many of these, then we go to the macroscopic scale, which is our scale. This, for instance, here, salt. Human try always to classify things. We are not happy if we cannot classify things we have. So, can we classify materials? Of course we can. But there is no single way to make this classification. The simplest probably is to go for the properties. So, metals, ceramics, polymers, composites, or semiconductors are 5 groups of materials that have very different properties. So it can be quite easily separated, into categories. Also, we go for classification depending on the kind of order or the range of the order present in the material. Then we talk about amorphous materials, single crystal, or polycrystalline. In the case of amorphous materials, there is no long range order. In the case of single crystals, we have short and long range order. In the case of polycrystalline materials, we have also long and short range order, but not uniformly all over the material. We have like regions. Inside the region is order, but from one region to the other, the configuration or the arrangement is slightly different. And finally, I would go also for a classification based on the different applications we can have. Biomedical, electronic, energy, magnetic, structural, functional, as you want. There are so many applications. Let's finish this short introduction with a challenge. Okay, it's not very difficult. It's easy. I suggest you, or I ask you to select an object in your environment, whatever you want, a table, a chair, a paper, whatever you want, and investigate what material it's made of. Yeah. Then think on this same sorry, I'm dyslexic sometimes. Then think on the same object, but in 3 different moments of the history. If you select a table, there have been tables from the antiquity, from the old times till now. If you select the TV screen, of course, only from mid 20th century, let's say 1950, 1980, 2000, or something like that. So select 3 moments and analyze how are the materials that are involved in the fabrication, the design and fabrication of this object. Don't try to go very deep inside. We will go back to this exercise, so don't worry at this point whether you get a lot of information or not. It's as simple as it sounds. Select an object, look for materials it's made of, and That's all. List them. No more. Okay? 3 points, 3 milestones to make it not so long. And if you need some inspiration or you can use something as a suggestion, in my website you can find various examples of timelines elaborated by other groups of students in the same course and some in other subject. Okay, so that's all for this introduction. Now we have more or less focused what is going to be the main topics to be tackled within this course, and now we can begin to move from this subatomic, or really from this atomic scale to this macroscopic scale, so going from the atom to the solid. So that's all for now. See you in the next lesson.